Big data is absolutely everywhere in our modern world. We are constantly creating vast amounts of digital information every single day. Just think for a moment about the sheer volume of social media posts generated globally. Consider also the detailed online shopping records that track our preferences and purchases. Furthermore, an increasing number of smart devices, from phones to home appliances, generate continuous streams of operational and sensor data. This data originates from a multitude of diverse sources. It arrives at incredible, almost unimaginable speeds. The sheer volume of this collected information is truly astounding. This entire phenomenon, characterized by volume, velocity, and variety, is what we collectively call big data. It certainly presents significant new challenges, but also unlocks immense opportunities for businesses, research institutions, and scientific endeavors. Why is this truly massive accumulation of diverse data so critically important today? The primary reason is that it holds incredibly valuable insights, often hidden deep within its complex structures. Companies, for example, can meticulously analyze this data to understand customer behavior much better than before. This deeper understanding helps them to personalize products and services effectively. Scientists across various fields can analyze complex patterns and correlations within large data sets. This analytical power can lead directly to groundbreaking new discoveries in areas like medicine or climate change research. Governments, too, can leverage big data to improve essential public services for their citizens. They can use it to make cities smarter, more responsive, and more resource efficient. Therefore, effectively managing, processing, and analyzing big data is absolutely crucial for driving innovation and maintaining a competitive advantage in today's rapidly evolving digital world. Traditional data processing tools and legacy systems often struggle significantly when faced with the scale of big data. These older tools were simply not designed or built for handling such enormous quantities. They often cannot effectively manage the wide variety of different data types encountered. These types include unstructured text from documents and emails, images from various sources, and videos from surveillance or online platforms. The sheer velocity or speed of incoming data streams also frequently overwhelms these conventional systems, leading to bottlenecks. Consequently, new, more powerful technologies were urgently needed to address these limitations. These technologies had to be inherently robust and reliable. They also needed to be highly scalable to grow with data volumes and cost-effective to deploy and maintain. This pressing need directly led to the development of powerful distributed frameworks like Apache Hadoop and Apache Spark. Understanding the fundamental concepts of big data is undoubtedly the vital first step in this journey. However, mastering the specialized tools designed to handle and analyze it effectively is the crucial next stage. This essay will aim to explore two of the most key technologies in this domain. These influential frameworks are Apache Hadoop and the versatile Apache Spark. We will carefully examine how these complex systems actually work under the hood. We will learn about their core architectural components and their specific functions. We will also discuss many practical real-world uses and applications of these tools. By the end of this discussion, you should have a clearer understanding of how these advanced tools can simplify the often daunting task of big data processing. This foundational knowledge opens up many doors to exciting possibilities in the realm of data-driven decision-making and innovation. Apache Hadoop emerged as a groundbreaking software solution specifically designed to tackle the big data problem head-on. It is a completely open-source framework, which is a significant advantage. This means that its source code is freely available for anyone to use, inspect, and modify. Hadoop allows for the highly efficient distributed processing of exceptionally large datasets. It achieves this by operating across extensive clusters of interconnected computers. These computers are often standard, off-the-shelf commodity hardware rather than expensive, specialized machines. This architectural choice makes Hadoop a remarkably cost-effective solution for organizations of all sizes. Furthermore, Hadoop can effortlessly scale from just a few single servers up to thousands of machines, consistently offering a high degree of fault tolerance and system resilience. The fundamental core idea that underpins the entire Hadoop framework is conceptually quite simple, yet incredibly powerful. Instead of undertaking the massive and slow effort of moving enormous volumes of data to a single powerful centralized computer for processing, Hadoop cleverly reverses this. It moves the necessary processing tasks directly to the locations where the data already resides within the cluster. This approach is a classic divide and conquer strategy applied to data. The large dataset is initially split into many smaller, more manageable chunks or blocks. These individual chunks are then distributed widely across the various computers making up the cluster. Each computer or node in the cluster then processes its assigned portion of the data in parallel with all the other nodes. This massively parallel processing capability significantly speeds up complex analytical tasks that would otherwise take many days or even weeks to complete on a single machine. The development of Hadoop was heavily inspired by influential research papers published by Google in the early 2000s. These seminal papers described in detail their innovative distributed file system, known as Google File System, GFS, and their MapReduce programming model for parallel computation. Based on these ideas, Doug Cutting and Mike Caffarella created Hadoop around the years 2005 to 2006. It was initially developed as a core component of the Nutch open-source web search engine project designed to handle the massive data involved in web crawling and indexing. The rather whimsical name Hadoop was actually chosen by Cutting, inspired by his young son's beloved yellow toy elephant. The technology quickly grew far beyond its origins within Nutch. It rapidly gained prominence and eventually became a prestigious top-level Apache Software Foundation project, fundamentally revolutionizing how organizations approached large-scale data storage and distributed processing globally. The Hadoop ecosystem, as it exists today, is much more than just a single monolithic software tool. It is, in fact, a comprehensive collection of many related software projects and utilities. These various projects work together harmoniously to provide a wide array of functionalities crucial for big data management. Some of the most key components include the Hadoop Distributed File System, HDFS, which is specifically designed for reliable distributed storage of huge files. Then there is MapReduce, the original parallel processing engine built for Hadoop. More recently, yet another resource negotiator, Yarn, was introduced to manage the cluster's computational resources effectively. A thorough understanding of these core components and their interactions is absolutely key to truly grasping the immense power and versatility of the Hadoop platform. We will explore these essential elements in greater detail in the subsequent sections of this discussion. The Hadoop Distributed File System, more commonly known by its acronym HDFS, serves as the fundamental storage backbone for the entire Hadoop framework. It has been meticulously designed from the ground up to store exceptionally large files with high reliability. When we say large, we are typically talking about files that are terabytes or even petabytes in size, far exceeding the capacity of single disks. HDFS achieves this by distributing these enormous files across a multitude of individual machines that form a Hadoop cluster. It accomplishes this distribution by breaking the files down into smaller, uniformly fixed-size blocks. By default, these blocks are typically 128 megabytes or 256 megabytes in size. These individual blocks are then carefully replicated across different machines within the cluster to ensure robust fault tolerance and data reliability, even if some hardware fails. HDFS operates based on a classic master-slave architectural pattern, a common design in distributed systems. The master node in this architecture is referred to as the name node. The name node holds the critical responsibility of managing the entire file system namespace, which is like the directory structure. It also meticulously controls all access to files by various client applications. Crucially, the name node maintains metadata indicating exactly where each block of every file is stored across the data nodes. The slave nodes, on the other hand, are called data nodes. These data nodes are the workhorses that store the actual data blocks on their local disks. They are responsible for performing the physical read and write operations on these blocks, as instructed by the name node or directly by the clients. Data nodes also regularly report their operational status and health back to the name node. One of the most significant and defining features of HDFS is its inherent and robust fault tolerance capability. As mentioned earlier, data blocks are replicated by default. This standard practice means that multiple copies of each individual data block are strategically stored on different data nodes, ideally on different racks within the data center. The default replication factor is typically 3, meaning 3 copies of each block exist. Therefore, if one data node happens to fail due to hardware issues or other problems, the data it held is still readily available and accessible from the other nodes that store its replicas. The name node is designed to detect such failures promptly. It then automatically initiates the process of re-replicating the lost blocks from the existing valid copies onto other healthy data nodes. This proactive mechanism ensures high data durability and continuous high availability, which are absolutely critical for any large-scale data storage system. HDFS is specifically optimized for handling large sequential data access patterns rather than random access. This means it performs exceptionally well when applications need to read entire large files from start to finish. It is therefore particularly well suited for batch processing workloads, which are very common in the domain of big data analytics and reporting. However, it is important to note that HDFS is not designed or optimized for low latency random access to many small files. Trying to read small, specific pieces of data from many different files quickly is not its forte. You can think of HDFS as being analogous to a massive industrial warehouse. It is excellent for efficiently storing and retrieving very large pallets of goods. Conversely, it is much less efficient if you need to quickly locate and retrieve a single tiny item from a specific shelf. This deliberate design choice makes HDFS highly effective for its intended purpose of supporting large-scale data analysis. MapReduce stands as Hadoop's original and foundational data processing model, a true pioneer in the field. It is essentially a programming paradigm, a specific way of thinking about and structuring distributed computations. This model allows for massively scalable, parallel processing of data across the entire cluster. The core concept of MapReduce is actually quite simple and elegant, despite the complexity it manages. It primarily involves 2 distinct main phases of computation, the aptly named map phase followed by the reduce phase. Developers using MapReduce are responsible for writing the custom logic within map functions and reduce functions. Hadoop's framework then takes care of all the complex underlying tasks, such as distributing the work efficiently, handling any unexpected hardware or software failures gracefully, and meticulously coordinating the overall job execution across the entire cluster of distributed machines. In the initial map phase of a MapReduce job, the input data, which typically resides in HDFS, is first logically split into smaller, independent chunks. Each of these individual splits is then processed by a separate map task running on one of the cluster nodes. The map task applies a user-defined function, the mapper, to its input split. This function's purpose is to transform the input data records into a set of intermediate key-value pairs. For instance, in a classic word count program example, a map task would read lines of text. It would then parse this text and output each distinct word encountered as a key, and the number 1 representing a single occurrence as its corresponding value. These generated intermediate key-value pairs are then systematically sorted and shuffled across the network, before being sent to the appropriate reducer tasks in the cluster for the next stage of processing. The subsequent reduce phase takes the meticulously sorted and grouped output that was generated from the preceding map phase. It processes these intermediate key-value pairs to produce the final output of the job. Each reducer task receives all the intermediate values that are associated with the same unique key from the mappers. They then apply another user-defined function, the reducer function, to this list of values. This function's role is to aggregate these values in some meaningful way to produce the final desired result. Continuing with our ongoing word count example, a specific reducer task would receive a particular word, the key, and a list of ones, the values representing each occurrence mapped for that word. The reducer would then simply sum all these ones together to calculate the total count for that specific word across the entire input dataset, contributing to the final aggregated word counts. Yet another resource negotiator, commonly known as yarn, was a significant architectural enhancement introduced in Hadoop version 2. Yarn functions as the critical cluster resource management layer for the Hadoop ecosystem. Its introduction effectively decouples the complex task of resource management from MapReduce's specific job processing logic. Before Yarn, the original MapReduce framework was responsible for handling both aspects, which limited flexibility. Yarn's more generic design allows Hadoop to run various different types of distributed processing frameworks, not just MapReduce, on the same cluster infrastructure. Yarn itself has a master component called the Resource Manager, which oversees global resource allocation. It also has node managers, which are slave components, running on each data node, managing resources locally. This architectural shift has made Hadoop a much more versatile and powerful big data platform, capable of supporting a wider variety of demanding workloads and applications. Section 5. Enter Apache Spark, the need for speed and versatility. While the original Hadoop MapReduce framework undeniably revolutionized the world of big data processing, it certainly came with its own set of inherent limitations. It was primarily designed and optimized for batch-oriented processing tasks, where latency was not the primary concern. Its significant reliance on disk storage for all intermediate data generated between map and reduce stages often made it relatively slow for certain types of applications. Iterative algorithms, which repeatedly process the same dataset, and interactive data analysis, requiring quick responses, were particularly affected by this disk I/O overhead. Consequently, the rapidly evolving big data community recognized a pressing need for something significantly faster. They also desired a more versatile and general-purpose processing engine. This clear and growing need directly led to the conception and subsequent development of Apache Spark, a powerful and flexible alternative and often a complement to MapReduce. Apache Spark is another prominent open-source distributed data processing system specifically engineered for exceptional speed, remarkable ease of use, and the ability to perform sophisticated advanced analytics. One of Spark's defining characteristics is its capability to perform extensive in-memory processing. This means that Spark attempts to keep as much of the working data as possible directly in the computer's fast RAM, or random access memory. This approach drastically reduces the amount of time spent on slow read and write operations to and from comparatively sluggish disk drives. As a direct and tangible result of this in-memory architecture, Spark can achieve performance that is up to 100 times faster than traditional Hadoop MapReduce for certain classes of applications. This speed advantage is especially pronounced for tasks that require multiple operations on the same dataset, such as machine learning training or interactive querying. The origins of Spark trace back to UC Berkeley's renowned AMPLab, Algorithms, Machines and People Lab, where it was first developed in 2009. It quickly gained traction and was subsequently contributed to the Apache Software Foundation, becoming a top-level Apache project in early 2014, signifying its maturity and community support. The creators of Spark had a clear vision to build a truly unified and comprehensive computation engine. This single engine was intended to efficiently support a diverse range of demanding data processing workloads. These workloads include traditional batch processing, interactive SQL queries, real-time streaming analytics, complex machine learning model training, and large-scale graph processing tasks. This innovative, unified approach greatly simplifies modern big data architectures. Users and developers no longer need to learn, deploy, and integrate multiple disparate and specialized systems for these different types of analytical tasks. Spark further enhances its appeal by providing user-friendly high-level application programming interfaces, or APIs, in several popular programming languages. These include Java, the functional language, Scala, in which Spark itself is largely written, the widely used Python, and the statistical language R. This broad language support makes Spark highly accessible to a diverse community of developers, data scientists, and data analysts. Furthermore, Spark integrates exceptionally well with the existing Hadoop ecosystem components. For instance, Spark can seamlessly read data directly from and write data back to HDFS. It can also leverage Yarn as its cluster manager, allowing Spark applications to run alongside other Hadoop workloads on the same physical infrastructure. This interoperability allows organizations to effectively leverage their existing investments in Hadoop infrastructure while simultaneously benefiting from Spark's impressive speed and advanced analytical capabilities, creating a powerful and synergistic combination for modern data processing challenges. Section 6: Spark's core RDDs, data frame and key components. The most fundamental and original data abstraction in Apache Spark, particularly in its earlier versions, is the resilient distributed dataset, universally known as an RDD. An RDD represents an immutable, fault-tolerant distributed collection of objects or data elements. These objects are logically partitioned and distributed across the various nodes that constitute a Spark cluster, allowing for parallel computation. RDDs can be created in several ways by loading data from various external storage systems, such as the Hadoop Distributed File System or Amazon S3, by referencing files stored on the local file system of the driver program, or very commonly by applying transformations to other existing RDDs. RDDs support two primary categories of operations: transformations, which create new RDDs, and actions, which trigger computations and return results, enabling the construction of complex data processing pipelines. Transformations are operations on RDDs that produce a brand new RDD as their output. Common examples of transformation operations include which applies a function to each element, which selects elements satisfying a condition, and which combines two RDDs based on a common key. A crucial characteristic of transformations in Spark is that they are lazy. This laziness means that Spark does not execute these transformations immediately when they are defined. Instead, it internally builds up a directed acyclic graph representing the lineage of RDDs and the sequence of operations. Actions, on the other hand, are operations that actually trigger the execution of these computations on the cluster. Examples of actions include which returns the number of elements, which brings all elements to the driver program, and which writes the RDD's content to storage. When an action is called, Spark evaluates the entire DAG of transformations to produce the final result, optimizing the execution plan along the way. This lazy evaluation strategy is key to Spark's performance and flexibility. While RDDs provide a powerful and flexible low-level programming interface, Spark later introduced higher-level abstractions called data frames and datasets to further simplify development and improve performance. Data frames are distributed collections of data that are organized into named columns, much like tables in a traditional relational database system, or data frames in popular data analysis tools like R or Python's Pandas library. This structured nature of data frames allows Spark to apply sophisticated query optimization techniques through its Catalyst optimizer, leading to more efficient execution plans. Datasets introduced subsequently are an extension of the data frame API. They provide a type-safe, object-oriented programming interface, effectively combining the performance benefits of Spark's optimized execution engine with the programming, convenience, and compile time safety of RDDs. This makes them particularly useful for applications written in statically typed languages like Java or Scala, enhancing developer productivity and reducing runtime errors. Beyond these core data abstractions of RDDs, data frames, and datasets, the Apache Spark ecosystem comprises several other key, tightly integrated components that extend its capabilities. Spark Core provides the fundamental underlying functionality for the entire Spark platform. This includes essential services like task scheduling across the cluster, efficient memory management for in-memory processing, and robust fault recovery mechanisms. Spark SQL is a powerful module that allows users to query structured and semi-structured data using standard SQL syntax or the programmatic data frame API. Spark Streaming enables the scalable, high-throughput and fault-tolerant processing of live, incoming data streams from various sources. MLlib is Spark's comprehensive machine learning library, offering a wide range of algorithms. Finally, GraphX is Spark's specialized API designed for graph computation and analysis. These integrated components collectively make Spark a truly comprehensive and versatile big data processing tool. Section 7, Hadoop MapReduce versus Apache Spark, a tale of two titans. Hadoop MapReduce and Apache Spark both stand as immensely powerful and influential distributed processing frameworks in the big data landscape. However, despite their shared goal of processing large datasets, they possess significant and noteworthy differences in their fundamental design philosophies, operational characteristics, and resulting performance profiles. MapReduce was the true pioneer in this space. It effectively established the foundational principles for conducting large-scale, fault-tolerant batch processing across commodity hardware clusters. Spark, emerging later, cleverly built upon these established concepts. It introduced crucial architectural enhancements, particularly focused on improving processing speed and offering greater versatility for a wider range of analytical workloads. A clear understanding of these key differences is essential for making informed decisions when choosing the right tool or combination of tools for a specific big data task, project, or ongoing workflow requirement. Perhaps the most widely discussed and impactful difference between MapReduce and Spark lies in their respective data processing speeds and how they manage intermediate data. MapReduce, by its original design, writes all the intermediate results generated by both the map tasks and the reduce tasks directly to a distributed file system, typically HDFS. This frequent disk input-output activity inherently creates significant latency, especially for complex jobs with multiple stages. Spark, in stark contrast, was engineered to perform the vast majority of its processing directly in memory. It only spills data to disk when the dataset becomes too large to fit entirely within the available RAM across the cluster. This predominant in-memory computation model makes Spark substantially faster than MapReduce, especially for iterative algorithms that repeatedly access the same data and for interactive data exploration scenarios where users require rapid query responses. Another key area of distinction involves the ease of use for developers and the richness of the available application programming interfaces. Programming directly with the MapReduce model can sometimes feel verbose and somewhat low-level. It typically requires developers to explicitly write custom Java code for both the map functions and the reduce functions, along with a driver program to orchestrate the job. Spark, on the other hand, offers much more concise, expressive, and higher-level APIs in a variety of popular programming languages, including Scala, Python, Java, and R. Furthermore, Spark provides an interactive shell environment available for Scala, Python, and R, which allows for rapid ad hoc data exploration and prototyping. Spark's rich ecosystem of built-in libraries for SQL querying, stream processing, machine learning, and graph processing further simplifies the development of complex analytical applications, significantly boosting developer productivity. The mechanisms employed for achieving fault tolerance also differ somewhat between the two frameworks, reflecting their core designs. MapReduce primarily achieves its fault tolerance by persisting all intermediate data generated during a job to the highly reliable HDFS. If a particular task or node fails during execution, the lost computation can be re-executed by rereading the necessary input data or intermediate data from HDFS. Spark RDDs, its core data abstraction, are inherently resilient. They achieve this resilience by meticulously tracking the lineage or the sequence of transformations that were used to construct them from the original input data. If a partition of an RDD is lost due to a node failure, Spark can automatically recompute that specific lost partition by replaying the transformations from its lineage graph. While both systems are robustly fault-tolerant, Spark's in-memory approach sometimes requires more careful configuration and resource management, especially for recovery in very large stateful streaming applications or complex iterative jobs. Section 8, Real-World Power, Hadoop and Spark in Action. Apache Hadoop and Apache Spark are certainly not just abstract academic concepts or theoretical frameworks. They are the real-world workhorses powering critical data operations in a vast array of diverse industries globally. Consider, for example, large e-commerce companies and online retailers. These businesses routinely use Hadoop's HDFS to store truly massive volumes of historical clickstream data, capturing every user interaction on their websites and mobile applications. They then analyze this rich historical data using batch processing techniques to gain deep insights into customer browsing patterns, product popularity, and conversion funnels. Subsequently, Apache Spark is often employed for its speed to power real-time product recommendation engines. This dynamic personalization, driven by immediate data, significantly enhances the overall user experience during their shopping journey. It also plays a crucial role in driving increased sales and customer loyalty. This strategic combination allows for both profound historical analysis and immediate actionable intelligence. In the highly regulated and data-intensive financial services industry, these powerful big data technologies are absolutely crucial for sophisticated fraud detection and risk management. Banks and credit card companies process literally billions of financial transactions every single day, generating an enormous stream of data. Hadoop can be effectively utilized to store and perform batch processing on these extensive historical transaction records, identifying long-term trends and subtle fraudulent patterns. Spark's advanced streaming capabilities can then be deployed to analyze incoming new transactions in near real time as they occur. It can rapidly identify suspicious patterns or anomalous behaviors that might strongly indicate fraudulent activity. This capability allows financial institutions to block potentially fraudulent transactions almost instantaneously. This proactive approach protects not only the bank from financial losses, but also safeguards its customers from the damaging effects of fraud and identity theft. The healthcare and life sciences sectors also derive immense and transformative benefits from the application of Hadoop and Spark. Medical researchers and bioinformaticians, for instance, frequently use Hadoop's HDFS to securely store and efficiently manage vast and complex genomics datasets, which can include DNA sequences and related medical information. Analyzing this intricate data at scale using distributed computing can lead to significant breakthroughs in the development of personalized medicine, tailoring treatments to individual genetic profiles. Spark's comprehensive machine learning libraries can be employed to build sophisticated predictive models. These models can help identify patients who are at a higher risk for developing certain diseases based on their data. Furthermore, Spark can assist in accelerating the complex drug discovery process by analyzing molecular interactions and simulating compound efficacy. This ultimately speeds up vital research and contributes to improved patient outcomes and public health. Telecommunication companies are another prime example of an industry that generates truly enormous amounts of operational data on a continuous basis. This includes detailed call detail records for every phone call and data session, as well as extensive network performance logs from various pieces of equipment. Hadoop is widely used by these telcos for the cost-effective long-term storage and in-depth batch analysis of these voluminous call detail records. This analysis helps in critical functions such as accurate customer billing, fraud prevention, and strategic network capacity planning. Apache Spark, with its real-time processing prowess, can be used to continuously process live network logs and sensor data. This allows telcos to detect network anomalies, predict potential equipment failures, or identify areas of service degradation almost immediately. This kind of proactive network maintenance and optimization significantly improves the overall quality of service for subscribers. It also enhances customer satisfaction by minimizing service disruptions and ensuring reliable connectivity. Section 9, the synergistic future Hadoop and Spark together and career horizons. It is critically important to understand that Apache Hadoop and Apache Spark are not necessarily mutually exclusive technologies. They are not an either-or choice for organizations. In fact, in many modern big data architectures, they often work most effectively and powerfully when used together in a complementary fashion. Hadoop, particularly its robust Hadoop distributed file system, provides an exceptionally reliable, durable, and highly scalable storage solution for a wide variety of data types. HDFS excels at persisting truly massive datasets, often petabytes in scale, in a very cost-effective manner using commodity hardware. Furthermore, Yarn, Hadoop's sophisticated cluster resource manager, is capable of efficiently managing and allocating cluster resources not only for MapReduce jobs but also for Apache Spark applications. This crucial capability allows organizations to seamlessly run their Spark jobs directly on their existing Hadoop clusters, maximizing resource utilization. This inherent synergy leverages the distinct strengths of both platforms to create comprehensive and powerful big data solutions. Apache Spark beautifully complements the capabilities of Hadoop by providing incredibly fast in-memory processing power. It also offers a rich suite of advanced analytical capabilities that extend far beyond traditional batch processing. Many contemporary big data pipelines are architected to use HDFS as the primary persistent data lake or storage layer for raw and processed data. They then strategically leverage Spark for the more computationally intensive tasks, such as complex data transformations, iterative machine learning model training, interactive ad hoc querying, and real-time streaming analytics. This intelligent combination allows businesses and research institutions to effectively handle a much wider and more diverse range of use cases. They can continue to perform large-scale batch processing with MapReduce if it suits the specific workload and existing skill sets. Simultaneously, they can harness Spark's significant speed and advanced features for tasks that demand low latency or sophisticated analytical functions, thereby providing a highly flexible, adaptable, and powerful big data ecosystem. Looking towards the future, the landscape of big data processing will undoubtedly see continued evolution and deeper integration between various technologies, including Hadoop and Spark. These platforms will likely evolve to become even more efficient, more user-friendly, and more tightly integrated with emerging data sources and analytical tools like AI and deep learning frameworks. Consequently, the demand from employers for skilled professionals who are proficient in both Hadoop and Spark, as well as related big data technologies, is currently incredibly high and shows no signs of slowing down. Companies across virtually all industry sectors are actively seeking talented data engineers to build and maintain data pipelines. They urgently need skilled data scientists to extract insights and build predictive models. They also require data analysts to interpret complex data and communicate findings. Expertise in these powerful tools opens up a multitude of exciting and often lucrative career opportunities in this rapidly expanding global field. In conclusion, to summarize the key takeaways, Apache Hadoop effectively laid the crucial groundwork for the entire field of big data processing, enabling organizations to manage unprecedented volumes of information. Apache Spark then skillfully built upon this solid foundation, introducing remarkable speed through in-memory computation and enhanced versatility with its unified analytics engine. Together, these two titans of the big data world form a truly formidable and comprehensive toolkit. They significantly simplify the inherent complexities involved in storing, managing, processing, and analyzing vast and diverse datasets. Mastering the intricacies of Hadoop and Spark empowers both individuals and entire organizations. It helps them to unlock invaluable, actionable insights that are often hidden within their data. This in turn drives innovation, improves efficiency, and supports more informed, data-driven decision-making in an increasingly competitive and data-centric global environment. The journey into the world of big data is indeed an exciting one, and these powerful tools are your essential and indispensable guides.